when you have your, I wanted to start with this one because this is a chain rule inside of a chain rule inside of a chain rule. It's a double chain rule. When you have powers with sine, cos, and tan, sometimes it's nice to rewrite them like this for the purpose of finding the derivative. So this is still f of x equals, but now I can tell that the tan 2x is inside the power of 4. And I can see that the 2x is inside of 10. So when we have a chain rule, the chain rule in words says, do the derivative of the outside function and keep the inside the same, and then multiply by the derivative of the inside function. So what that would mean here is the outside function is a 4. If you had just x to the 4, it's a simple derivative, it would be 4x cubed. But we have a tan 2x to the 4. Again, to start off with, it's simple. The 4 would come out in the front. You would keep the inside the same. Subtract 1 from the exponent. And then we have to multiply by the derivative of the inside function. The inside function is this tan 2x, which is another chain rule where the 2x is inside of 10. So we follow the same chain rule. The derivative of the outside function, well, the derivative of tan is secant squared, keep the inside the same, and then multiply by the derivative of the inside function times by 2. So the double chain rule just means you have to walk yourself through those steps more than once. Derivative of the outside function, keep the inside the same, multiply by the derivative of the inside function. And while I was doing the derivative of the inside function, I ran into another chain rule. So I had a new outside function, which I did the derivative of, and then multiplied by the derivative of the inside function. Okay. Whew. This is very typical of an IB question. That's why I wanted to do examples 3, 4, and 5. What they do is they give you a function, and then they never ask you to simplify something. Instead, they'll ask you to write it to look like something. So if I would do the derivative of h, normally I would say, oh, probably we use my quotient rule, keep the bottom the same, multiply by the derivative of the top, subtract, keep the top the same, multiply by the derivative of the bottom. Now, I wouldn't have to do this, but you see that it's a chain rule where the x minus 1 is inside the function. And when I do the derivative of the inside function, I just get 1. So I wouldn't have to do that 1, but I acted like it was a chain rule over the bottom squared. So squaring something that was already squared would put it to the power of 4. So normally if you were just asked to find the derivative, you would stop here without simplifying, be perfectly fine. Okay? But this question said, actually, we would like it to look like this. A number minus x over x minus 1 to some power. If I look at my top, it is not just something minus x. There is a lot more complicated things in it. I'm going to show you a hint or a strategy for simplifying in these cases. First of all, I want you to notice that in the numerator, there is this big thing minus this big thing. We basically have two terms that are subtracted from each other. When we talk about a term, it's things that are connected by multiplication. So these things are all connected through multiplication. These ones are all connected through multiplication. And there's a subtract sign in between. So I have something minus something. And in the something minus something, I notice there's an x minus 1 in the first something, and there's also an x minus 1 in the second something. if there's something in common, I don't think I've said something so many times in the start of the question before. But if there is something in common, you can factor it out. And the nice thing about what's in common is it's also the factor on the bottom. So what that will allow me to do is if I factor out 1x minus 1, on the top, can you see in the first something, we would be left with just 1x minus 1. Then I have a subtract sign, and if I took the x minus 1 out of the second something, I would get an x minus 2 and a 2. But that would be it, because the x minus 1 would be gone, and I don't need to write that extra 1, because that's just multiplying by 1. Close that square bracket with, technically I have 4x minus 1s all multiplied together on the bottom. Can you see that this one would cancel out with this one, leaving me with 3 of them? This is going to make your simplification so much easier. If you can factor out a common factor and it simplifies, you're already on the way to making your question and life easier. Now, when I look at what's left on the top, I would get x minus 2x and negative 1 plus 4. The negative 1 plus 4 is going to be 3. The x minus 2x is going to be minus x, and on the bottom, I'm left with x minus 1 cubed. So it's in the right form, where the a value happens to be 3, and the n value happens to be 3. This is one way that the IB goes, can you simplify? Like, that's an important thing in all of math, but usually in derivatives it's sort of like, we don't want you to just keep simplifying, it takes too long. Most of the time you can just leave your derivative as one step and be done, but sometimes it will be nice to simplify. So if they want you to simplify, this is their way of asking it. Rather than saying simplify and having a whole bunch of different answers and different people stopping at different places, they say, actually, we want you to simplify until it looks like this. This is type number 1 of them asking you to simplify. Type number 2 is the very famous show that question. In a show that question, they're basically telling you what the answer is in the question. It's like you turned to the back of the book and saw what the answer was. You just now have to make your question look like that. So if I was starting with this, I'd be like, okay, I want to find my derivative. My derivative would equal, I have a chain rule. My outside function is the cubed. So that 3 would come out in front, keep the inside the same, subtract 1 from the exponent, I'll write it like that right now, multiply by the derivative of the inside function, and then minus derivative of sine x is cos x. So a normal derivative question would be, just find the derivative. In a show that question, they're like, find the derivative, now I want you to manipulate. Can you take this, can you manipulate so that it looks like this in the end? Things that are not allowed in a show that question, you can't use the end before you get there. You can't assume that it works and then make it work because you assume that it works. You have to just, it's like a proof that only goes one direction. You have to start with this, manipulate this until you get this. And there's some strategies involved here as well. Okay? The strategy that I would use in this one is I would say to myself, I notice that there's a minus 3 cosec's. The thing that's going to causes me a little bit of like, ugh, is the cos 2x. I don't have any cos 2x's here. I don't like that part. But the minus 3 cosec's, that kind of matches up with what I have. And then I also notice that I have 2 terms here, and a 3 and a cosec's are in common in both of them. So I can factor. And when I factor, because I have a minus 3 cosec's in the answer, most typically, when I say, hey, what's in common between these two? Students would say, there's a 3 and a cosec's. Right? But in this situation, I'm going to factor out a negative 3 and a cosec's. Because this one has a negative 3 and a cosec's. And then see what's left. If I take out a negative 3 and a cosec's in the first term, I would have a negative 2 and a sine squared x. And in the second one, it would now be plus 1. And this is where you can use a show that to kind of help you decide what to do. There's hints. Show that naturally give hints. You'd be like, I would normally factor out a 3 cosec's, but because the hint had a negative, I factored out a negative 3 cosec's. Now, this part and this part look the same. I now think if there was only a way that I could make those the same, I would be done. And then, oh yeah, you're all looking at the formulas off on the side. Does that work out perfect? Yeah. You look on your formula sheet, that does work out perfect. And we are done to show that question. So show that questions, you start them the same way. Oh, it's a derivative. I want to show that the derivative is equal to this, so it's telling me I have to find a derivative. I find my derivative, and then I need to manipulate, because there's no way that if someone said simplify, you would never think of adding a cos 2x when simplifying. But if it's a show that question, they can make you manipulate it to whatever they want, but it also gives you a hint for what you should make it look like. All right, so if on the next page there are 2 more show that questions, I will leave those ones for you to try. I most likely have videos of these online, so if you want to look up the answers, you can find them. Just want to talk about this one for a little bit. It has the show that. So you start with this, and then you manipulate it to show that it looks like that. And then this question, and every time I underline stuff in the notes, these are specific IB math command terms. The famous hence or otherwise is slightly different than hence. If you have a hence question, you have to use what was given to you right before to do the next part. If you use any other technique, they give you 0. In a hence question, it's like you have to use what you just figured out. In a hence or otherwise, you can use, they're telling you what you just figured out is a hint. That would probably be the easiest way to do it. But if you want to do it another way, right? If you want to get up during the exam, walk across the room to Eddie's paper, coffee down, come back, and hope nobody notices, right? Not a good strategy. Not a good strategy, right? But that's part of the otherwise. So actually, the otherwise is using any other math that's legal under exam writing settings. You are not allowed. It said otherwise. I'm allowed to now use any strategy whatsoever, including cheating methods. No, that would not count. Oh, that'd be a nice IB loophole. But no, you're going to try it out? It said otherwise, right? We should, oh, now, I want to take out the IB curriculum and legalistically break down what otherwise says, and if there's a contradiction, no. So that's the otherwise command. Right? This one has just just the hence. So you have to use this result in order to say, right? And hence, find all the values where the derivative is undefined. Well, if I look at my derivative, something is undefined when you divide by 0, and you see that -2 would make it undefined. So we can already do the hence part of this question without doing the other part. And sometimes they do a hence part in an exam question because the student actually can't do the first part, but they want to check something else. And if they have a hence, you can still do the second part, even if you screwed up the first part. And if they do a show that, they're like, even if you screw that up, at least in part B, you're using the right equation. Because sometimes you make a mistake, and then you have to do the next part with your mistake, and it gets worse. And then you do the next part with your mistake of your mistake, and it gets worse. So they sometimes do questions there. Contrary to everything else you'd expect. They're actually nice sometimes. I'm sure you but whatever. You sometimes feel like these IB questions are like, oh my goodness. They just hit me over the head with something hard. Then you turn to part B. Oh, they found something harder to hit me over the head with. But sometimes in questions they are nice, and this is an example. Okay. Oh, of course the recording had problems. Maybe I'm lucky. I won't be fired from the IB program today. What the heck?